This is problem 28, the last of the QHack 2023 quantum coding challenges, and this one is entitled Ising Uprising. Now in this problem, what we have is a closed spin chain similar to the one we had in the previous problem, where these spin half particles are exposed to a magnetic field. So the Hamiltonian that described this system is this ZZ interaction between adjacent particles and then this term with a magnetic field strength of H. So what we're asked to do in this problem is to find the ground energy of the system using VQE. So what we need to do is first construct our Hamiltonian, whose expectation value is going to be our cost function, and then we need to implement a circuit for an Ansatz that is expressive enough to be able to converge to that ground energy state. Okay, so let's take a look and see how we can implement this in pennylane. So the first thing we do is we import pennylane and numpy. Then we're going to use 4 qubits because we're told that this chain consists of 4 particles. We're going to define a function called create Hamiltonian that is going to take as an input just the strength of the magnetic field. So here, to define that Hamiltonian, we're going to do it with the Hamiltonian class within pennylane, which requires the coefficients and the observables for the complete expression. So first let's define the coefficients for the ZZ interactions. So that's just a list of length n and just all values equal to -1. So we just do num qubits times -1. And then the observables are going to be this ZZ interaction. So we can use the poly Z gate in pennylane for wire and then tensor product with a poly Z on the next wire. But since it's a spin chain, this needs to loop around. So we can do this modulo num qubits. So that way, when we reach to the last wire, so wire number 3, this becomes 4, and then modulo 4, it just becomes 0. So it loops around. And then we do 4 wire in range number of qubits. Okay, so those are the observables and the coefficients for the ZZ interactions. And then for the magnetic field terms, we just need to do the same, but here instead of this -1 coefficients, we need to have coefficients of -h. So all we need to do is just replace this with -h. And then the observables are just poly x on each of the qubits. And then our complete list of coefficients is just the sum of the two. And same for the list of observables. And here we're just going to return the Hamiltonian for these values we have defined. Okay, now we're going to create a Q node for our model, which is going to be our Ansatz. And since it needs to be expressive enough, what we're going to do is just implement it using the basic entangler layers block that we saw in a previous problem. So here in the documentation, you can see here that this basic block for just one layer applies some rotation gates and then this ring of C0 gates, and we can define which type of rotation gates we want. So what we're going to do is do one layer for Rx gates, one layer for Ry gates, and one layer for Rz gates. So that's what we have defined here. So the same 3 blocks, but here the rotations we're applying are Rx, Ry, and Rz. And we're going to pass to each one of these the right number of parameters. And then here what we're going to return is the expectation value of the Hamiltonian that we're passing here. All right, now we're going to define a function that we're going to call train that takes as an input just the strength of the magnetic field. And here's where we're going to define our gradient descent algorithm. So again, pennylane has this gradient descent optimizer function, and we can just pass a step size of, let's say, 0.1. We define a maximum number of iterations of, let's say, 1,000, and some convergence tolerance of 1e-4. Then we're gonna define a variable called Hamiltonian, which is just basically going to store what we get out of this create Hamiltonian function. So that's our pennylane Hamiltonian object. And then we're going to initialize our parameters for our Ansatz circuit. So we can do that with the random function in NumPy. And here we're going to create 3 sets of variables, one for each of this entangler layer circuits. And then we're going to do it for 3 layers on each of these and a total of 4 qubits. And then we're going to say that this requires grad true so we can perform gradient descent. And now we're going to do our for loop that updates our parameters and gets the previous value of the cost using the gradient descent optimizer step and cost, which takes our model that requires to pass the parameters and our Hamiltonian. So we pass the parameters that are going to be updated, and then our Hamiltonian is the variable we define up here. And then we can get the new cost just by passing to our model the new updated parameters. And here we can create a condition just to print our results as we do gradient descent, and also a condition that if our new cost minus our previous cost is smaller or equal than our tolerance, we can break this for loop. And then this function is going to return our parameters. Okay? And then for an input of 1, which is the first input that is given in this problem, we're going to run our model. And here I made a mistake. I placed this parentheses in the wrong location. So let's rerun that cell. Look at our model training. And here we have it. After 600 steps, we've reached a value of minus 5.21, which if we look at the result here is very close or within the greater tolerance of minus 5.226. And then we can run it for that second input of 2.3. And here we can see that we reached minus 9.66 after around 120 steps, which is also very close to the expected solution. So I hope this was helpful, and I hope you enjoyed this series of videos. And as always, let me know if you have any questions.